Let's review again the notation for derivatives. First of all, when we start out with our function, y equals f of x, we are talking about a function with an independent variable of x and a dependent variable of y. So our function is y equals f of x. Using prime notation, the first derivative we just say is f prime of x. Using Leibniz notation, we say derivative of y, dy, over dx. So the derivative of y with respect to x is dy dx. Now we can look at higher order derivatives. We will not be doing that too much too soon, but our function is called f of x. Using prime notation, we'll say f prime of x is the first derivative. And we just talked about dy dx is also the first derivative. If I want to talk about the second derivative using prime notation, I'll say f double prime of x. And in Leibniz notation, we'll say d squared y dx squared. This notation will look a little confusing until we get used to it, but for the most part, we'll be looking at first derivatives and eventually second derivatives. We can find third derivatives. That would be f triple prime of x, or d cubed y over dx cubed. Beyond that, it gets difficult to write all the primes, so they're just going to put a numerical superscript number. So this would be the fourth derivative of f with respect to x, and d for y over dx to the fourth. If you write that in general, the nth derivative is f superscript n of x and nth derivative of y with respect to x. Okay, again, for the most part, just focus on knowing and understanding the first and second derivative notations. Okay, let's also add one other thing to this. We've talked about function, first derivative, and second derivative. But our function could sometimes be called position. Oftentimes, this is denoted with the function notation s of t. The derivative of position is velocity. Remember, our first derivative, another name for it, is the instantaneous rate of change, or the instantaneous velocity. So oftentimes our first derivative will be talking about velocity. From s of t, velocity is the derivative of s of t. Okay? And we'll denote velocity with a v of t function notation. Of course, this could also be in Leibniz notation, ds dt. All right, the derivative of velocity, we will learn eventually, is called acceleration. So acceleration is going to be the derivative of velocity or dv dt using Leibniz notation. Okay. Moving on, let's look at interpreting using words, using units, interpreting points, inverse points, and derivatives, and the derivative of the inverse. So first item is, let's look at the fact that in this scenario, the cost in dollars of building a house, A square feet in area, is given by the function C equals f of A. State appropriate units for all values and interpret by explaining the meaning of each. So I have a note here that says cost should be is in dollars, and our cost in dollars is the dependent variable. Area in square feet is the independent variable. Let's take a look at units for each of these four equations that are written here. So it says f of 2,000 is 300,000. Remember, the input of the function is area in square feet. The output, 300,000, is cost in dollars. So for this first point in question, the XY units are square feet and dollars. Now remember, let's look at part B. If you think about an inverse, F inverse, well, that means we're swapping our X and Y ordered pair. So this time, the 248,000, which is the input, is in dollars, and the 1,800, which is coming out, is in square feet. Let's take a look at part C. F prime of 2,000 is 1,000. The input of F prime is area. The output is a rate of change, an instantaneous rate of change. So the units associated with the 1,000 are dollars per square feet. The next item, D, says we're doing the derivative of the inverse. So what I want you to think about is this inverse point in terms of dollars per square, or dollars for input and square feet for output. So for this item, $248,000 is the input, but this 1/800 is the output, is the slope of this inverse function. Taking a look at the units, remember we're going to swap the units around, so instead of dollars per square feet, we're going to get square feet per dollar. Okay, now let's look at interpreting each of these points. So f of 2,000 is 3,000. Coming back to part A. A house with area of 2,000 square feet costs $300,000 to build. Okay, pretty straightforward. Taking a look at B, remember this is an inverse, so things are swapped around in terms of swapping X and Y. So a house costing $248,000 has an area of 1,800 square feet. All right, part C. F prime of 2,000 is 1,000. Remember, the results here, this result of 1,000 is dollars per square feet. All right, but how do we say this? We say the cost to build a house is increasing at a rate of $1,000 per, that should be square foot. Okay. So to increase the area from 2,000 square feet by an additional square foot is an additional $1,000. Okay. Last one, part D. F inverse prime of 248,000 is 1/800, or 1 square foot per $800. So for a home costing $248,000 to build, each additional 1 square foot increase will cost an additional $800. So in section 2.4, there's a lot of interpreting. Function values, inverse values, instantaneous rate of change values, and sometimes there are a few inverse instantaneous rate of changes. Okay, coming back to the derivative function. So you have learned the derivative at a point, a f of a. This only allows you to determine the instantaneous rate of change at x equals a. So for example, or the definition there is f prime of a is the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, when we evaluated this, we came up with a numerical value representing the instantaneous rate of change at a f of a. Okay, but what if we want to know more than one instantaneous rate of change on a function? We are now going to start looking at the definition of derivative in terms of x. So instead of one value, we'll find a general function for the derivative in terms of x. This way, if we have the function, we could find the rate of change at any x value you choose. What is the definition of derivative? In general, it will be f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Take a look at the difference between the general definition of derivative on the right and the value definition of derivative on the left. The only difference is that a is replaced by x, leading to a general function. So, in our last class, we looked at slope functions for given graphs, of polynomials in particular. So, if the function is a constant, or a linear, or a quadratic, or a cubic, what did we find out about the derivative? Well, if a constant function has a slope of 0 all the time, then its derivative has a slope of 0. So this is my f prime of x. That function, I can tell you right away, is f prime of x equals 0. For the linear function, what is the slope of this line everywhere? Well, it is 3/2. So at y equals 3/2, I will have a constant line representing the derivative everywhere. F prime of x equals 3/2. Okay, what if I have a quadratic? Well, we learned you find the horizontal tangents. That's where you have 0 slopes. And then you look and you say the slopes are negative and the slopes are positive, but I know it was a linear function. The question is, what linear function is this? I don't actually know. So we're going to have to find that using the definition of derivative. This cubic has some zeros. I'm taking a stab at where those are. I don't know exactly. But I know somewhere in between there's a greatest negative rate of change. And we have positive slopes, 0 slopes, negative slopes, 0 slope, positive slopes. So we have to start high, go through our 0, come down to our low, back up. That was a really terrible graph. It should look more like a nice quadratic. So we'll kind of fix that up. So that's supposed to be a nice quadratic. What quadratic is it? I don't know. I'm going to have to use the definition of derivative. So remember, the definition of derivative, the limit as h approaches 0 of f of x plus h minus f of x over h. We're going to use that to find the derivatives. Okay, I'm not going to have enough time to do any of those examples, so I'll put up another video and we'll chat in class tomorrow.